The big problem that we have out there is language. And language. A lot of people think that anyone who does language, does clarification of language, is doing word wizardry, word salad, semantics.
Minor stuff, wasting their time.
Yeah. It's like, for them, it's just noise coming in the ear and coming out the other. So what we do, we start with, I'm going to be starting today with some of the questions and comments people made, because that's going to lead into the subject matter of today. So I'm going to work it in reverse. Instead of answering the questions at the end, today we're going to start by answering questions that people asked, because they're related to the subject matter of today. Okay. So let me start with this. What we do in this channel, we like to put what is known as the universal movie.
I do have to say before we start, I like that when I look up rational science, this is the first thing that shows up.
What?
We're the only people doing rational science.
Oh yeah, that's Anyways,
Okay,
here we have the universal movie, and what it is, you have to imagine the universe. Every atom in the universe has location. That's all it has. Okay? And in the next microsecond, billionth of a second, quadrillionth of a second, every atom in the universe is at a different location. So everything moves from location to location to location. And in one of those frames, all we have is location of every object in the universe. So think of that as a 3D movie. And one of the problems we have is that a lot of people, especially dissidents, they use concepts as physical objects, specifically the ones that I circled there: plasma and ether. The establishment also uses field, but those are the three words that are always used as physical objects.
Well, the thing that the concept that's used the most as a physical object would have to be motion. Movement is moved.
Indirectly.
Indirectly, movement is moved the most.
Yeah, if you say to people, is motion a physical object, they'll say no. But if you say, is plasma, ether, field, or energy a physical object, well, people have problems with that. They think these are physical objects. And as you can see, I put them at the bottom because those concepts are dynamic concepts. They take at least 2 frames of the universal movie. Whereas the ones on the top in yellow, they only occupy 1 frame of the universal movie. Okay, so that's essentially what we're trying to show there. And what we'll see today is some of the questions that I'm going to be answering today are related to dynamic concepts, which people treat as physical objects. That's the whole problem. Okay, so it is a language problem. And again, for them, it's just noise in their ear. They say, well, I came here to do physics, not grammar.
Yeah.
We have to do physics is 150% semantics.
I wish it weren't, but
you gotta define your terms. You gotta tell us what you mean by the words.
It's not really, but it has become that way.
Yeah,
Since people have abused it for so long, now it's become the first thing that you look at.
Absolutely.
It's just because due to the abuse of the English language,
English and any
language that is done in.
And it's important to note that mathematics is only a language. I mean, people say, well, the language of physics is mathematics. Well, is the language of physics Chinese? Is the language of physics Greek? You know, it's Greek to me, and so that's the language of physics. No, the language of physics is illustration if you're going to be explaining a mechanism. Okay, so we got to keep that in mind. So one fellow says the following. Let's get started here. He says the following. He says, seems unfair, your definition of plasma. Right? Plasma is a highly ionized gas. And then next slide, you define ionization. Okay, ionized is past tense. Okay. It's already ionized, finished, like he imagines it. If chemical reactions are occurring in air, it doesn't make it any less of a gas. Okay? So what is this fellow saying? Well, he's saying essentially this. He's saying, look, here we have ionized gas or ionized atoms on the left-hand side. You take a snapshot of it, which is the one you see on the right-hand side, right? And he says, well, it's already ionized. The one on the right is already ionized, ED, finished. Yeah. And the question is, if I take a snapshot of ionized gas, ionized atoms, can we say that plasma is a static concept because I was able to put it in a snapshot? Okay, so that's the question. And the answer is no, because the word plasma already embodies motion. Let me repeat that, because I don't think that's sunk in so easily. The word plasma already embodies motion. And what we should be doing is really maybe defining plasma so that these people understand is instead of ionized atoms, we should be calling them constantly ionizing atoms, because they're constantly being ionized. Plasma never stands still, because if it does, all the electrons recombine with their atoms. And so, and it turns into gas. So we cannot stop the word plasma. What this person is trying to take a picture of is not atoms or gas. He's trying to take a picture of ionized or ionizing. And you can't. That requires 2 frames of the movie. And here, let me
give you... Is it because you have to have the
because it works
with the ion and then without it?
No, the issue is that plasma is a mixture, right, of atoms together with normal atoms that have not been ionized, that have not lost their electrons, right? Yeah. Together with other atoms that have lost their electrons, if we're going with the quantum mechanics version, which is really the one these people have in mind. So some atoms have lost their electrons, some atoms have not. And it's a soup, it's a mixture. Something is stimulating that ionization constantly.
But if someone took a picture of has already lost its electron ionized gas. They have a picture of just the part where it's where the electron is out.
Yeah. I hear you. I understand. Right? Yeah. Now what?
Can you point to that and say that's plasma?
No, because the word plasma means ionized, not gas. It means ionized, and you're trying to take a picture of a verb.
That's
so
it's like a fine line.
Well, no, here. So here we can see it. I think you'll understand what my argument is. What semantics, word wizardry, word salad. Okay, here's a little word salad for you. Okay, here we have it. On the left-hand side, we see a running boy.
Yeah.
Okay, that's a movie. I put it in a single.
I can see it now.
Okay, on the right side, you have a boy. And you say, well, I took a picture of a running boy.
Yeah.
No, you haven't taken a picture of running. You took a picture of boy. Okay?
Yeah.
Running requires, you can't take a picture of running because running always requires 2 frames of the movie.
Ionized gas is still just gas?
Well, it's ionized. You're trying to take a picture of ionized. You're trying to take a picture of running.
But if you were to take a picture of ionized gas, you'd say that it's just gas because you're trying to add the running to the gas.
Yeah, because you're really not taking a picture of gas itself, because it's not, the question is not whether you took a picture of gas. You took a picture of what is known as plasma, but the word plasma has that adjective in front of it. It's called ionized.
But if someone brought a picture of plasma to you, it would be as if it were the boy that were in one frame running. You would say it's just gas.
You could say that, but even there, you would need to have a comparison to, without the ionization.
No, you don't care. You don't need...
No, what I'm saying is, if you try to explain it to an ET, right, and you say, look, there's a bunch of little balls there, and smaller balls, which are the electrons, they're out. He won't know what he's looking at. He's looking at a bunch of balls. That's all it is, really, for him.
He'd just say it's gas, right?
Yeah, at best he would say it's a gas or just a bunch of balls. Yeah. You would have to explain to him what it is. But my point here is another one. My point is that you're trying to take a picture of a verb. You're trying to take a picture of running. You're trying to take a picture of ionizing.
Well, you said something interesting yesterday that I still was trying to wrap my head around. The adjective? Yeah, you said that physics, and I don't know if everyone here agrees with this. Let's see if we get a show of hands. Physics, I don't know how you phrased it, but something like does not require or does not need adjectives.
Yeah, you can't use, there's no such thing as a dead cat, like in Schrodinger's cat, right? There's no such thing as a live cat. There's no such thing as a green tree, as a brown house. There's only a thing called house.
Superfluous poetry is what adjectives have become.
You cannot put an adjective in front of a noun for the purposes of physics. In physics, we point to an object and we don't say it's the greenhouse. No such thing as a greenhouse. There's only such thing as a house. Green is an adjective, and now you're qualifying it. You're comparing it against brown, blue, and other types of houses. So you're making a comparison. If you just want to point to the object, you say house, cat, dog.
So you're saying if this were a court of law, that'd be grounds for an objection. Objection used an adjective. But you said adverbs are fair game?
Yeah, well, I'm saying adjectives do not come together with nouns in physics. In physics, you point to the noun, to the cat, to the dog, to the rock, to the tree, to the house. You point, and say chair. You don't say that's the brown chair. No such thing as a brown chair in physics.
But
now,
is
as
it because
an object.
Is it because we don't care? Is it always unnecessary information? Does it just muddy the water?
It muddies the water.
Are you adding motion? What are we doing here?
Well, people say, well, I can take a picture of ionizing atoms or ionizing gas. No, you don't realize that you're trying to take a picture of ionizing, not of the gas or the atom.
Yeah.
Okay, and here it is. This is the definition. Now, there you have it. Plasma. Constantly ionizing atoms. I don't know how else to define it so that people don't try to work around it. If it's constantly ionizing, you can't take a picture of that, because as soon as you take a picture of that, you don't have plasma. What you try to do is take a picture of ionizing, and you cannot remove the word ionizing from the word plasma. That's the issue.
We have someone that says constantly balding head. Balding is a process. You can't just point to a bald head because he's balding.
Yeah.
I think he's talking about you.
Okay, yeah. There. Okay, and here's another aspect to our good old plasma, okay? A lot of people say, well, Bill, it's a state of matter.
Mm-hmm.
No.
No.
Absolutely not. Let me show you why. You cannot use plasma as define it or even qualify it as a state of matter, okay? Yeah. State is a static concept. There's no such thing as state in two frames of the movie.
I think we can all agree about that.
Okay, so state is a static concept, plasma is not. So here, let me show you.
By that definition, would color be a state?
Well, let's look at this. Here we have it. Here we have the different states of matter: solid, liquid, and gas. None of those three require motion.
You got a GIF here. Can we get the ionized? Can I get the ionizing in a picture?
See, we have solid, liquid, and gas. The words, right? There's no such physical object called solid. Solid is a category. There are many solids. So solid is a category. So is liquid. So is gas. But ionizing is something that involves motion. It cannot be a state. You cannot say plasma, the fourth state of matter. No, state, there's only three states, and those are solid, liquid, and gas, because those three words do not embody motion. Whereas the word plasma does embody motion, so plasma is not a state. And I know that destroys the religion of all people of the electric universe who also think that electricity is a physical object when electricity is something in motion. So it's a movie.
Where do you think the problem would be? Are you just seeing such discrepancies with the categorization that you're just convinced that at some point down the line of their presentation they're going to mess it up, or what?
Well, they do mess it up. They do mess it up because the electric universe says, for example, just an example here, gravity is electricity. Yeah. And they try to explain it with electricity. No, gravity cannot be electricity because you have to identify the physical object, the mediator of gravity. And you cannot say electricity is the mediator because electricity is something already in motion. You got to whatever you present, a tree, a dog, a line, whatever, it's got to be static. You got to show it and say that's what's going to serve as the mediator of gravity. You cannot say electricity because electricity is already in motion.
Well, what's wrong with something already being in motion?
Because the way
the universe is already in motion.
Because in physics, in science, right, the scientific method, you have to present the objects and the definitions first. First step, objects and definitions. And you have to point to the object so we know who are the actors. And this guy says, I'm going to present a boy running. Okay. Or a running boy. No, you get. Please present the boy. Then you can put him in motion. But please present the boy first.
Well, I'm sure they haven't broken down electricity to the minute level that you have either. But are you saying that because they would have to also take electricity and say, okay, what is electricity? What is it that's moving?
Yeah.
So and they don't do that. They still have to break down electricity into the static and the movement of the static.
In fact, it's even worse in the sense that they already know No? Quotations?
Yeah.
What electricity is. Electricity is what quantum mechanics gave to the electric universe and to all these people who use electricity as a mediator. And that is, an electron bead moving from atom to atom. That's electricity according to the electric universe and according to the establishment. And so the question is, what is the object? Well, the object is the atom. And then you ionize it. In other words, you have that electron bead leave the atom, go to another atom, and it goes to another one. And that process is called electricity, according to the establishment.
I don't want to go too deep into this if you don't want to, but just as a quick last question, how would you conceptualize the pull of gravity? Are they saying that there's wires of atoms between everything?
No, it gets even worse.
No,
because
I don't want to know.
No, you want to know. I want to let you know whether you like it or not. No, what they say is positive and negative.
Where are the atoms?
Don't worry about that. Because it's all conceptual. They say positive attracts
negative.
Hold on.
If electricity is an electron going from atom to atom, whatever an electron is, right? But that implies that there's rows of atoms.
And what you have is the electron. No, in fact, they got rid of the atom too. All they have is electrons moving now, without any.
Now we're just shooting guns.
Just shooting beads. So the electrons go from positive, towards a positive pole.
Yeah.
And
where's the pull?
I don't know.
You didn't do your homework.
It only goes one way.
Okay. I think I'm good on the electric universe.
Okay, another fellow goes in there and he says the following.
It's funny when I need you to explain crazy theories as if they're supposed to make sense.
Yeah, right. Here the fellow says Newton didn't base his gravity equation on anything static. Again, he based it on Kepler's laws, especially equal area swept at equal times. Okay, the point here is that this fellow doesn't understand what static means. Okay, and that's the whole issue here. So let's go with that. Let's find out why Newton's equation is static. Gravitational equation is static.
Yeah.
Okay, that's what we need to explain here. What do we mean by static when we say Newton's equation is static? Okay, and I'm going to give you two answers to that. One is related to distance, and the other one is related to weight. Okay, so here let's go with the first one. Okay, here let me get rid of this one here. I got rid of the wrong one.
Can't bring it back?
I guess not. It doesn't matter here. Really what it was the... maybe I can't get it back, but let's get this one. It doesn't matter here. Okay, so because this is essentially the breakdown of what I was going to say anyways.
Yeah.
On the left-hand side, what you have is the distance of physics. And on the right-hand side, you have the distance of mathematics. The distance of physics is the one embodied in his gravitational equation. It's attributed to Newton, so we're just going to use Newton as the reference. So the gravitational equation, Newton's gravitational equation, which you see the equation up there, that one's got a static distance. That's the distance of physics. That means there's separation between two objects, two masses. Okay, the one on the right is something totally different, which is Newton's second law of motion. Okay, and sometimes they say, well, we make the F on the left-hand side equal to the F on the right-hand side. Big error, because qualitatively they're not the same, and you can see there the differences between them. In the case of Newton's gravitational equation, you're talking about the distance between two objects. It's a static separation. Static. There's no motion. We don't count meters. We don't count centimeters. We don't use meters in physics. That's mathematics. And that's what you have on the right-hand side. The right-hand side, what you have is motion. And you're going to count how many meters the guy moved or the one object moved. The first one is between two objects. The second one, the one on the right, is a single object moving away from something or towards something. So we're looking at the motion of one object. And so we're talking about distance traveled by one object, not the separation between two objects. Okay, and that's what we have in Newton's second law there of motion. And you can see some of the differences there. So when I say that Newton's gravitational equation is static, I'm referring to the fact that that you're talking about a separation, a physical separation between two objects. Okay? And that's what we mean by static. And if you go down the line there, if you go to number 6, there it says, distance is a measure of weight. Weight is a static concept. Okay, weight is a static concept. Why? Because you don't need to move. In fact, if you move in space anywhere, you change your weight. Okay, your weight changes instantaneously as soon as you take a single step. Okay, so never take a step because you're going to lose or gain weight. Okay, in physics. And of course, they could never answer why that is the case. Why, as soon as you move in space, why does your weight change? And here I'm going to illustrate that for you, okay? See if we can do this. Okay, astronaut farther away from the Earth weighs less. If we could weigh him out there, he'd probably weigh 25 kilograms. Closer by 50 kilograms, and down on Earth he probably weighs 100 kilograms.
Hey,
why?
You gave the 50-kilogram guy more ropes. That's cheating.
Yeah, more ropes. Why? Because he's closer to the Earth. Every rope in his body is, from every atom in his body is connected to every atom on Earth. The closer he gets to the Earth, the more the ropes tug independently. So if you take that astronaut to infinity, so to speak, all the ropes come in together, and that's why gravity is so weak, because it acts like a single rope, like a single coaxial. As he gets closer and closer to the Earth, he has this acceleration, because the closer he is to Earth, the more ropes tug independently. They're not on the same axis. Okay, and that's what's happening. But for a given point in space, for a given distance, static distance, if I were to freeze that frame, the astronaut has a given weight. As soon as he moves an inch closer to the Earth, he weighs more. Okay, that's what it is. And so weight is a static concept because force in Newton's equation is a static concept because distance is a static concept.
Which is confusing
because we're all
because...
static.
Well, the reason someone would think, in fact, even if someone asked me if weight were a static concept, I would have guessed no. Because if you put him on a scale,
he's got to push down.
Yeah, it's like the running boy, the weighed down man.
Okay, so let me point out to what you just said. Yeah. Okay, you step on the scale. Okay, as you press down, right, you're getting closer to the Earth. Your weight, the scale starts going up, right? Because as soon as you put 1 foot, it goes, 10 kilograms. But as soon as you put your whole weight, it goes up higher, right? Yeah. Because you're pressing down on the scale, you're closer to the center of the Earth, right? But once you stop, right? Once you stand absolutely still, hopefully you don't move in any direction. Yeah. You could achieve that. At that point, you have weight for that location only. As soon as you move a little bit to the side, whatever, your weight changed. Okay, so if you could stay absolutely still without moving anything, if you could still do that, then you would have weight only for that location because you have the same distance with respect to whatever other atoms are on Earth. Okay, another issue here. Fellow says, gravitational field is what the experiment of Cavendish proved. We talked about the Cavendish experiment the other day with the measuring of the value of the constant G. Okay, field is the space. Field is a space. Yeah. Space I thought was nothing, but he says field is a space of the gravitational interaction between two bodies with mass. Furthermore, it could be the infinity of space. Space is infinite? What do you mean space is infinite? Is space a physical object or not? If it's a physical object, it's finite. And if it's infinite, it can't be an object because an object is that which has shape. So he's got a contradiction saying infinity of space. No such monster in physics. Okay, again, these are words that they fed him in his brain and he just accepted it from the monastery. He's got to think that there can't be infinity of space. Either space is an object and is finite, or it ain't an object, in which case the word infinity doesn't even apply. Okay, it is space of interaction between two magnets, whatever that is, the space of interaction, okay? It was proved by Maxwell. I like the fact that they prove. Proof means that someone convinced you.
We finished. He already proved it.
Yeah, no, but proof means that someone convinced you of something. That's all proof means. The word proof belongs to religion. In fact...
what I always say is proof is persuasion.
Yeah, it means
the
that
way to say it.
someone convinced you of something, and that's why you believe it, and it's proof to you, not to your neighbor.
Anytime you hear the word proof, just listen to the word persuasion.
Yeah, it means I want to win over you in the argument, so I say they proved it, and you're wrong.
It's creepy. I mean,
you should accept it.
It's a little disorienting when someone makes that comparison. That proof is persuasion, but it's like I wish that weren't true. Because everyone likes the word proof. It's just it's solid.
Because proof means
it's grounded.
That my religion is stronger than yours.
It means you can finally put a stake in the ground and I can build a house here. No, it's still wobbly. No, it's still persuasion. There's nothing.
Okay, another fellow says a force is when an object moves. Okay, that's a force. An object moves because it interacts with another object or field. So we have a force interacting with a field. Great, we have two concepts, force with field. This one is called energy, another concept. And it's what makes things happen. Yeah, I guess. We have all these concepts interacting. See, this is the
force
problem.
Is when an object moves.
But see, this is the issue. The issue is that all these people are using concepts. Force, field, energy are all concepts, mathematical concepts, and they have them interacting. They say, oh, the force interacts with the field and the field with an energy, or we call it energy. It's all concepts, mathematical concepts that have no place in physics. Physics, we have to explain the mechanism, why a pencil falls to the floor, so to speak.
It's a weird way of saying, of talking. It's like if I said, my field of view engulfed something.
Yeah,
it's good
poetry.
It's a weird way to talk when you're using these concepts interacting with the world. No, your field of view didn't engulf the world.
But when you attack that, they say, "Oh, you're doing word salad. You're attacking it from a semantic point of view." Well, yeah, because you're doing word salad if you're introducing concepts as objects. You're doing the word salad, not me. Okay, so here's another fellow. He says, light and magnetism are proof of the existence of electromagnetic ropes. Well, keep in mind that the rope is not something we prove, okay? We make an assumption. We make an assumption that there is a rope-like mechanism, a mediator between two atoms, okay? And with that, we're going to explain, okay, a mechanism. So we haven't proven the rope. We're not asking you to believe in the rope. We're saying, look, accept the rope in order to understand the theory founded upon it. Period. That's all we're saying. Okay, we're not saying believe in the rope and this you got to accept it, and we're not here to convince anyone. We're here to explain mechanisms using.
Let's just understand. We really care that everyone understands the theory, and then after that we don't care.
Right.
And to understand
their own.
But to understand the theory, you have to. It's almost like plausible deniability, or whatever the term is, where you have to accept certain assumptions for a time. Like, okay, let's
to understand the theory.
Yeah, just to understand. Like, if you wanted to explain the hole in the window, okay, let's assume
a cat did it, went through the wall.
Could that explain this?
Right.
All the things?
And that's the way physics should work. Okay. Okay. The following says, actually, it was Leibniz over 300 years ago who thought that the Earth could have arisen from a sun. We were talking about the fact that Earth was a star. Okay.
And you put your stake in that.
And it says, Jeffrey mentioned in one of his videos talking about one of the fellows who came up with this stellar metamorphosis, or claimed to have been the originator. No, he wasn't. It was Alexander Oparin. But this fellow says, look, Leibniz even beat Oparin. Okay. And if you look it up, there's the reference there, Conservapedia. Leibniz supposed the Earth to have been once a star. Okay? And he wrote that in several of his books. This is to say a molten body, an incandescent liquid, without explaining how it got into that state. Okay? What's the issue? The issue is that Leibniz, 300 years ago, he did not have all the information at his disposal, what we have today, of new ideas of how the sun works, how a star works, okay? That's the first issue. So he had his ideas, and he said, it could have been a star, but he had no way. If we would have bring Leibniz today, he would not be able to justify those statements.
You're saying he just said it offhand, like...
He kind of had an idea. He said, look, it probably was a star, but he would not be able to justify it in a way that you would understand how it got to the state where it is today. In fact, he thought it was a molten some kind of molt that's somehow hardened, and turned into the Earth. Okay, but he would not be able to explain it in today's terms. So in that sense, I don't know if we can give Leibniz credit. We can probably give Oparin a little more credit, even though Oparin said it in 1926. And if you look at Oparin's statement, he also probably should not be given all the credit, because he also thought of it as a molten. He got that from the nebular hypothesis, where you have this cloud that condenses. And so he's also using that as a basis. But here we are 100 years later. I think we can do better than Oparin, okay? So this is the nebular hypothesis. Here you can see a little bit of illustration of that, okay? You have the sun and you have the planets. And according to the nebular hypothesis, they were all gases just roaming around that somehow condensed through gravitational processes. But the main thing I want to point out is you can see all those little planets, or the little gases that are going to turn into planets. They're residual gases. The big gas is the sun, and the little gases are the ones that are going to turn into planets. And here you see our planet as one of those, okay? There's our little gas bulb, and it turns into our planet eventually. In other words, it condenses.
I don't delete those. I might need those for a question I have.
Okay, I'll keep that one there. But see, you can see what's happening. The little cloud there, that's going to be the Earth. Okay, one of those, or any of those, are going to be planets. Okay?
Yeah.
And I just want you to focus on that, because we have a different theory. Okay, that I'm going to tell you about it right now. You can see this turns into the Earth. Okay? Okay, so that was the notion that they had. What are we saying instead? We're saying that if we looked at the gases, the way we think happened, the condensation, the Earth was a much bigger cloud than the sun. Why? Because in order to make iron, Earth apparently has iron in its center, it had to be a much bigger gas cloud and a much bigger sun that eventually crushed or compressed hydrogen into helium and higher elements, and eventually into iron. Our sun cannot produce iron according to the calculations. So they say in order to produce iron, you need a much bigger sun than a much bigger star than our sun.
But aren't we still using the nebular hypothesis?
We are, but then the question is whether the gas cloud that made the Earth was the same gas cloud that made the sun. That's one issue. Whether there was a gas cloud millions of years or billions of years before the one that made the sun, and that was our Earth in this vicinity. It condensed, it created our Earth, it was a star, then that star condensed into a planet, what is known as a black dwarf, and eventually there was another gas cloud which turned into a sun, and our Earth was in the vicinity and was captured, and it started rolling around. So this is what I'm going to show you here, the sizes of the different gas clouds. The three gas clouds that I can compare them in size. Here it is, okay? I'm saying Jupiter, small gas cloud, and it condensed into what is Jupiter today, which is a star that never ignited because it doesn't have the mass to ignite. The sun was a bigger cloud, but it was not big enough to make iron. There was not enough matter to compress it so that it condenses the center into iron. The Earth had to be a much bigger cloud if it's going to crush all the atoms or crunch them so that it compresses them into iron. So that's in general what I'm suggesting. Okay, that's the proposal. And we can add to this what is known as the iron catastrophe. Okay, and that is that when a supernova exploded nearby somewhere, maybe it threw some iron or some heavier elements like uranium or even radon or whatever into our neighborhood, and that's why we find it still in our neighborhood. We find these elements on Earth, and this is more or less what the iron catastrophe is all about. It says, look, you've got this planet, and it was in a molten state, okay? And so what happened was that a lot of those elements, heavier elements, sank to the center, Okay, there was iron crushing, banging against other iron. Some of that fell into the earth and then fell into the center of the earth. That's another proposal. I don't buy too much into the iron catastrophe, only because there had to be quite a bit of iron floating around. And I don't think that's how the iron got into the center of the earth. I think the way it got in there is that the earth was a star and crunched it on its own, crunched the hydrogen to helium into higher elements, silicon, etc., all the way to iron. And then, yes, you can produce a center that is iron. And that would also explain why the earth is differentiated. In fact, I'm saying that any round object in the solar system, right? Any round object, any spherical object, except the flat earth, right? Any of those was a star of some kind. And in the case of smaller ones, like, little pebbles like, Mercury, even so, or the moon, I think they were the size maybe of Jupiter, maybe a little bigger.
But those ignited or did?
No, I don't think they ignited. I think that's why they don't have any gases on their surface. No, they have no surface. Yeah, they are, but they don't have gases on their surface, which would indicate that maybe they were not big enough or over the centuries, gazillions of years, they lost their atmosphere.
Even if they don't ignite, I'm sure just by the way the gravity works on these celestial bodies, that differentiation seems like an inevitability.
Yeah.
Eventually, just with enough time, you're gonna have those layers.
In fact, when Jeff pointed this out some time ago, 2, 3, 4 years ago, I can't remember now when, but I liked the theory. For the first time in my life, I came in contact with this theory. Finally found out it wasn't Jeff's, but O'Parent's. He already had said it. And I was able to explain two things I could not explain since the days of high school, and that is why they're round and why they're differentiated. And round and differentiated, that's a star. So the Earth was a star that turned into a cinder known as a black dwarf. That's the way I look at it.
Did I hear you right? You don't think uranium and these heavier elements were made on Earth?
I'm not sure about that, because there's another problem with that, and you should keep this in mind for anyone who wants to tackle the problem. And that is, you find all this stuff on the surface. The question is, how did it get on the surface of the Earth? Okay, now was that brought in by some asteroid?
But you find iron on the surface too.
Yeah, also, but see, not in the quantities that you would find in the center of the Earth.
Obviously.
So there
you
could
still
be other
find chunks of it, so it's not perfectly differentiated. Let's put it like that.
The Earth is differentiated and quite perfectly differentiated. The question is, why do we find some of these elements that should not be on the surface? Why do we find them on the surface? And was that brought in by asteroids or comets or whatever?
Is it that the Earth is differentiated except the surface? Is the surface like the wild card?
That's where the iron catastrophe comes in. The iron catastrophe just says there was a lot of metal flying around because there was a supernova that threw all this garbage into our neighborhood. And here was the Earth, or the sun, condense our star, right? It was condensing, and at some point, maybe a lot of this garbage fell in there and just ended up on the surface of this cool star that was trying to cool in its last moments. And that's why it's still on the surface, or somewhere on the surface. Maybe some of it was still in a molten state or in a gaseous state, and some of that penetrated a little deeper. So if we go, a kilometer down the Earth, we'll find some iron, some...
Hold on, does it have to be so complicated? If there's tectonic activity and there's volcanoes,
could bring it from the surface.
That's what I'm saying.
So there's a lot of processes you can consider.
There's a lot of motion on our rocks that's sending stuff from the bottom to the top.
Well, the point here is there's a lot of theories that you could implement. Say, well, why is it here? Well, because of this theory. Why is this that? Because another one. My general point is that all these round objects had to be some kind of gas that condensed and turned them into a star. And it could not have been the same gas that made the sun, because the Earth had to be a much bigger gas cloud than the sun when it formed many billions of years before our sun. The Earth was there when the sun picked it up.
Yeah, but the Earth already shed its husk, which is a lot of gas, to make the sun. So the sun right now is using what the Earth shed off.
it could be some of that gas that from our surface. Well, I'm sure a lot of it is, but I can't say that the big gas cloud that made the sun came all from the Earth.
Maybe. Where else would it have come from?
Well, it could have been a supernova exploded through that gas or that garbage into our neighborhood when the Earth was still rolling around, in the middle of nowhere. So, the point is there's a lot of theories to put in there. I don't buy the nebular hypothesis for the planets. It is for the sun, and it would be for the Earth when it first formed. But what I'm saying, the Earth must have formed before the sun. The Earth was a captured black dwarf. The sun was the last member of our solar system. That's my point. Okay, let's move on here. Anyways, all those are theories for you to consider.
Wait, I had one more question.
Okay. Let's see. What you got there?
Because the way I conceptualize our solar system is, since other solar systems are so far away, we're almost like a contained unit. When you talk about
self-contained,
self-contained, because I almost have this notion, not a theory, but this notion that there's no such thing as a supernova flinging matter from one solar system to another. That's almost impossible because they're just so far away. Well, you even talk about the bird's beak and stuff like that.
Okay, but you have novas and supernovas, and I can imagine that when they shed all that skin, that's a lot of
across solar systems too, like between galaxy kind of stuff.
Well, for us, the distance from here to the nearest star is a long ways away. Yeah. But for a galaxy or for a star, that's just a couple meters away in a sense. So you have to remember one thing. Another one is that the magnetic field of our star, of our sun, extends way beyond Pluto. So and you say, Pluto's out there in the middle of nowhere. It takes hundreds of years to get there, for the sun. It's got its magnetic field around that and beyond.
Because I was wondering, assuming our solar system were self-contained, and assuming you can't turn matter into nothing, nothing into matter, the basic assumption of our whole thing, then would that imply that our solar system repeats over time?
What do you mean repeats?
Well, because if the sun explodes, scatters, matter all over, then the nebular hypothesis starts again. You start convening to make a new sun.
Yeah.
Like if the sun explodes and destroys the Earth, you're gonna have all this just kind of matter floating around in our solar system. Then it's gonna start the process all over again of reconvening into the Earth sun.
Yeah.
That's gonna turn into a black star, and then our now sun will black dwarf. Yeah. Then our now sun will come after that. Is it just like
in other words, now the sun becomes a planet.
Yeah, but is it just a repeating process?
I think to some degree it is, and maybe you can pitch in there, supernovas that could be throwing garbage also into the neighborhood. So, all I'm saying is we have to look at all these theories and put them all together. We can't just go with the nebular hypothesis and say, there was a cloud, and a big cloud was the sun, and the little clouds was the Earth. I don't think that works. I think if you're going to do this, you're going to have to look at a lot more variation. You're going to have to include stuff like the iron catastrophe could have happened, supernovas throwing garbage into our neighborhood, molten state where comets and asteroids bring garbage into your planet and what's going to become the planet. I think we got to look at all these processes and try to, get a better idea of how our solar system was really formed.
Well, I asked because one of the most interesting topics to me is the repeatability of the universe. Assuming there is no, beginning frame or ending frame.
Right.
If it's just kind of eternally there, then you almost have to, at some point, explain the whole, I don't want to say life cycle, but like universe cycle. Like, how is it that this wasn't the first Earth?
It wasn't the first universe.
I
think that it's an ongoing process.
But it's fun to explain that whole process because it isn't linear.
No, of course not. It's
like
cyclical.
Human history on Earth is linear, but the universe, the way it kind of recycles itself, isn't. And it's just always interesting to me. How is it that when the sun explodes, that a new Earth is made?
Well, even worse, like I say, there never was a first human being in the universe. Yeah. Because when you go farther back in the past, there had to be some human somewhere in the universe, and if you go 1 million years in the past, there had to be some human somewhere in the universe.
It gets really sci-fi.
And when you start to think of it, if matter cannot turn into space and space cannot turn into matter, the universe has always been there, and there was never a first human being. We always have this thing about origin, starting. You're born. That doesn't happen with the Father Universe. He was always there.
He's still going.
And we don't understand that.
It's weird.
It's very hard.
The way I always explain it to myself, if we were once, that means we will always be.
Yeah.
It's one of those weird sci-fi things.
And some human will come after us. Somewhere.
It gets trippy and weird.
Okay, a couple more issues here. One fellow says, Bill says the black stuff is space. This is irrational. The black stuff is the ether. Well, he hasn't told us what the ether is. He just says the black stuff. I guess he's referring to space, right? And black stuff is not stuff. That stuff that you say is black, that's known as space, and space is not a thing. So it's not stuff. Okay, so again, you have to tell us what the ether is. And unless you can define the ether or point to it, one of the two, either it's a concept and you define it, or it's a thing and you point to it and say that's the ether. You got to show us some kind of shape, a drawing, a picture, a photograph, a
mock-up. Isn't it always a sea of balls?
Huh?
Isn't the ether always drawn as a sea of balls?
I don't care. They can draw it as a ball, but then you got to tell me what's outside the ball and give me a shape. Okay, that's the tricky part.
Can't win with you.
Okay, so here we have another fellow also brings up the ether, and he says, I'd really like to know whoever said the ether was made of particles. That was me.
Yeah, well, everyone said that.
Ether being particles is complete nonsense, okay? The only ones I know of the electric universe quacks, they think it's made of imaginary neutrino.
What else could the ether be if not balls?
Well, this is the issue. The issue is this fellow you can see as all ether is.
Yeah.
The all ether is. How do we define an ether is? Here, let me define ether is for you, and that'll tell you everything. An ether is a person who cannot define the word ether or tell you what it is.
Yeah.
That's what an ether is. Never has an etherist who came to this channel ever been able to define the word ether or point to it. Put a picture and say, look, here's the ether over here. Look at it and tell, and now you'll know what the ether is. It doesn't mean the true, genuine, super duper ether. It's the ether he's got in his brain.
Yeah. How does he conceptualize it?
Yeah, I need to know how he conceptualizes it.
Because I would like to conceptualize it as well in that matter. So, even just to understand it. Like, is it a sea of balls?
We cannot guess what you have in your brains. If you're going to present the ether, first of all, you have to decide whether it's a concept or an object. If it's a concept, define it. Tell me what the meaning of the word ether is according to you. If you think it's an object, draw it, put a picture on the internet and say, look, Bill, there's the ether. Okay? And of course, if you put a shape, you got to tell me what's on the background, because a lot of people, like this fellow says, the ether is space. Okay, but space is not stuff.
Well, that's the thing. There's a very low chance that we mean the same thing when we use the word space. When he says space, we understand nothing.
Yeah.
Nothing. So but in his mind, he's got something else.
Okay, then put it there. If you think it's a thing, just draw it and tell us what is the background that gives it shape.
You want to backdoor the space.